Okay, everyone, welcome to Errors, Effect Sizes, and Powers Part 2. And this time we're going to talk about controlling the two types of error and just get a quick review of them because I know it takes a few tries to actually make sense of errors. So let's just start with type 1 error real quick. Remember the type 1 error is where you reject the null hypothesis. You say the groups are different, but it's not correct. It's because you've got an unusual sample. Now, the way we control for type 1 error is simply by making up whatever alpha we want. Alpha literally is the probability that you have committed a type 1 error after you reject the null hypothesis. So in this slide, we have a couple of alphas, and I want you to pay attention to how this works. Normally, alpha is 0.05. It gives us critical values in a z-test of 1.96. If we want to reduce the chance of getting an unusual sample, we move the boundaries out. 0.01 for an alpha gives us cutoff values of 2.58. So by reducing alpha, it just becomes harder to get an unusual sample at that level. This says that 5% of our samples from the null hypothesis would show up significant. This says only 1 would. This says 1 in 1,000. Problem is, when you move those critical values out, that means you have to go that much further in order to find a significant value. So it actually protects against type 1 error very well, but it increases type 2 errors. So let's take a look at the next slide here. So alpha is usually 0.05 because that puts you at a fairly low rate of type 1 errors without making it impossible to detect differences. So type 2 error happens when you fail to reject the null hypothesis. You don't notice a difference when you should have. Normally, that's because you've designed a study that should produce significant effect. Maybe you've just got an unusual sample. Maybe you have some incredibly fit people running up the stairs and it barely budges their heart rate. But more often than not, when people don't get significant results that they expect, is because of what's called a low power test. So we're going to talk about power. We're not going to calculate it. There are ways of calculating it. But I just want to show you 4 things that influence power. So the idea of statistical power, which I'll probably just say power more often than not, is that there's a probability each time you do a test that you will correctly reject the null hypothesis. A test that has high power means that the researcher has set it up in a way to guarantee finding differences. Well, maybe not guarantee, but making it far more likely that you will find the differences that you expect. So it's important to understand this so when you're designing your own research someday that you know how to do high-powered studies. Now, power, there are 4 things you can do. 2 of them have to do with alpha, so we'll start with those. The first thing to do is let's not be too conservative with alpha. Remember that if you try to prevent type 1 errors, you can set alpha really low, like 0.1%. It means only 1 in 1,000 rejections will be a type 1 error. And while that sounds good, notice that it requires like over 50% more z-score to reject the null hypothesis. So you don't want to be too conservative with alpha. That's why we usually do 5%. Now, we're in an unusual era. COVID-19, the people who are working on things like methyl-quintuate treatments and things like that, they might actually be using alphas of 0.1 or 0.15 because we're desperate to find something fast. So they're going to be more sensitive to finding things that work. And then they'll follow up later with other tests to make sure they're not doing type 1 errors. So there are situations in which you want to be more liberal here and use a 0.1 or a 0.15. But those are pretty unusual circumstances. All right, here's another thing we can do. If you've been reading the text, you've seen this already. This is called a directional test or one-tailed test. And this is what you can do when you have a theoretical reason or prior research has given you a reason to expect the mean to go in one direction and not the other. So in our research, for example, our students, we have our bowl here with a mean of 70, And if I send people running up 4 flights of stairs, I have no expectation at all that the heart rates are going to go down. So what I'm doing is I'm putting all of my alpha on that side. And if I do that, all I have to do in step 1 is say that my alternative hypothesis, H1, is that the mean of my group, I think it's going to be greater than 70. Normally, we do two tails and we put the inequality sign there, so we say it's not equal to 70. The directional test, I'm saying it's greater than 70. Okay, you can do the flip side. Let's imagine that I have a different bowl here. This is a group of people with tachycardia, which is generally defined as having a resting heart rate over 100. So let's say that this population has a mean heart rate of 106, and I'm going to put them on a beta blocker regimen. There's nothing about beta blockers to make me think it'll actually make their heart rates go up. So what I'm doing in my test here is I'm going to put all of the critical area on the left side. And in step 1, when I write my hypotheses, I'm going to say my alternative hypothesis is that the population I'm sampling from, that is the population of people on this dosage of beta blocker, they're going to wind up less than 106. They're going to wind up less than their original. So that's what a one-tailed test is. It's a directional test because we have every reason to believe the sample mean is going to go in one direction and not the other. Just so you can make sure you see how this helps us, this graph shows side by side what it looks like if you have a two-tailed alpha of 0.05 versus a one-tailed alpha of 0.05 in a t-test, holding the degrees of freedom constant. Over here we've got the two-tailed alpha 0.05, and it shows us the critical value is negative 2.042 and positive 2.042. So it's taken the alpha 0.05 and it's split it in half. Now if you did the exact same study, but you knew in advance beta blockers are going to reduce, not increase, you could put the entire alpha on the left side. And here with the one-tailed alpha of 0.05 and the exact same sample size, our critical value is actually negative 1.31. So we've gained 0.8 T's, and that's going to make it quite a bit easier to detect a difference, and it won't have any impact on the rate or the probability of the type 1 error. All right, so those first two things, deal with alpha. Next one is a pretty simple thing to do most of the time. If you can get a big sample size, you're going to benefit yourself in a number of ways. The first thing to do is remember that sample size is related to the shape of the distribution like that. And in fact, if we look over here in this, you can see that the first thing it does is it shrinks your critical value of T. So a sample size of 12 in this case produces T critical values of 2.2, whereas if you have an infinite size or even over 100, your sample size is close enough to be pretty similar to Z, so your critical value would move over here. So by increasing the sample size, they brought the critical value in, meaning you don't have to get as far apart to get significance. Okay, in addition to shrinking T, it also, T critical, it increases the T test. So if you look at this formula here, you should see where sample size comes into play. It's right there. What I've done below is I've created two things that hold the three elements constant up here, but they vary according to sample size. Both of them have the same difference, 74 minus 70, but when you get that from a group of 9, the T value is 1. And as you should be able to infer from this, that's nowhere near close to significant. We don't have the exact critical value down here, but it's going to be over 2. And this doesn't even get past 1. Now here, exact same difference between the means, but this came from a sample of 81. Solve that, and you get a sample size of 3. I'm sorry, you get a T value of 3. And T is very clearly significant because with a sample of 81, you're going to have a critical value of t that's somewhere around 2. So that is about 50% higher than it needs to be. In both cases, the difference between our sample mean and the population mean is 4 points. The reason it's so much more statistically significant in the lower case is that it's so much more challenging to get a 4-point difference with 81, right? Because sample means don't distribute as much. So large sample sizes, you can almost always do that unless you're working with really rare things. They help you by shrinking the critical value of t and increasing the test statistic. Final thing. Increase effect size if possible. Now, it's not always possible for reasons I'll explain later, but it's usually something you can do, and you can do it because what it really is a product of dosage. So here in this example, I'm going to look at dosage in terms of like the flights of stairs that someone might run up. So in this case, I'm holding standard error constant. So in both of my examples, I have a sample size of 9 this time. But I'm guessing that if we had a group of 9 go up to like 1 flight of stairs, we might get a heart rate of about 74. If we had a group of 9 go up 3 flights of stairs, we might have an average heart rate of 86. So what I'm saying is that the number of stairs has a direct impact on this value right here, and that makes the numerator a bigger number. Calculate through those. It looks like the top one comes out to a t of 1. So having a person climb 1 flight of stairs is probably not going to have as much of an effect as going up here. So that gives us a t of 4, which again would clearly be significant. Now, the reason this is significant is because we had a big effect. We did not get significance just because we had a high sample size. So that's actually kind of impressive. And that's the way we wanted to work. But how do we know if we have a good effect size? Well, I introduced in the one sample t-test video the concept of effect sizes. We're going to come back to that to wrap up. So an effect size is basically the follow-up to a hypothesis test. Your z-test or t-test, if it's significant, it tells you there is probably a difference, but it doesn't tell you if it's a big difference or if you're just using a big sample size. So we follow up our tests with a measure of effect size, and that tells us, okay, is our statistical significance due to something that's big and meaningful and important? And the one that we use for z-tests and t-tests is called Cohen's d. We'll find some other effect sizes later in the term, but we're going to use this one. All right, so those are my t-test values right there. The difference between Cohen's d and a t-test is that d uses standard deviation, whereas t uses standard error. So, here we go. So I've solved d. This has a t value of 1. That's not significant, and it's because of a small effect. This has a t value of 4. That is statistically significant, and it's because we have a pretty solid effect. Okay. So moving a group of people up to 74 is only a third of the standard deviation. Moving them 16 points is 1 1/3 standard deviations. So that's pretty big. So how do we know how big effect sizes are? Well, this is kind of a scale to use right here. I got this idea from Wings, believe it or not. Okay. So if you go get Wings, you know that you can describe wings using regular English words, going from, not very hot to pretty hot to screaming hot. Effect sizes, we kind of use words like that too. So we're less concerned with what the actual numbers are usually than what they tell us. And so we use those words right there. So when you find your d value, you kind of compare it to this and you say, my first d was a 0.3, and that example, that wasn't very big, so no wonder it wasn't significant. In my second example, it was 1.3, and that's very large. And in fact, that can go on up infinitely. So I'll leave you with this. Increasing power is how you prevent type 2 errors. And there are 4 things you can do to increase your power.